Welcome all. I'm Michael Schertz. I'm coming to you from beautiful Boulder, Colorado, to wherever you are, and I'll be talking about the Open Force Field Initiative today and our current efforts towards transferable force fields for biological and organic molecules. Now, what is the Open Force Field Initiative? So it is an open source, open science, and open data effort working towards improved molecular force fields and force field science. The focus is on developing new software, databases, and methods to enable the creation of better force fields, ideally across many force field efforts. And with these tools to construct physically based, chemically consistent force fields for small molecules and biomolecular systems broadly defined. There's 4 main labs, but with over 20 collaborating scientists across 10 total labs, if you include all the people who we're collaborating with. It's funded by NSF, most recently NIH, and by about 12 pharma companies, though usually a relatively small amount from each via the Open Force Field Consortium. So we're grateful to lots of folks. This is a real community effort. I'll only be scratching the surface of what's going on, but what's being done is due to a lot of people. I would specifically call out, I'll be talking about work from people doing QM fitting in these new molecular force fields, software infrastructure that make this all possible, and fitting to physical properties. I'll be drawing on work of all these people, and there's several other associated efforts in all of this. So how is the effort open? This is important. So it's open source. Everyone has access to this free toolkit for building and improving force fields. And it's MIT BSc so that it can be used just as well in industry as in academia. Open data, all of the data sets are collected and curated so that people can use them for their own efforts. And it's open science. Everything is done in the open, rapidly disseminated via GitHub, preprints, and websites. There's a number of, if some of the topics sound quite interesting, go to the website. There's a number of presentations linked there on a lot of these efforts by the scientists who are mainly in charge of them. So please check out the website. So some distinguishing scientific elements of the Open Force Field Initiative that I think are important. So using chemical perception to assign force field parameters. The force field parameters are dependent on the chemical environment alone. I'll talk a little more about this in the talk. Developing an infrastructure to rapidly evaluate the effect of parameters on physical properties of interest, to really automate the process of saying, how does this new parameter change affect all of the different physical properties? Creating workflows, fragmenting and generating QM data for the torsions and other valence terms. If you're trying to cover a very large chemical space as you need to for drug-like small molecules, you need to be able to calculate the quantum mechanics of the torsions of all of these. Curate and torsions, angles, bonds, all these bonded terms. Also, curate and generate experimental QM data sets for force field parameterization and assessment. Curating the data that is used to put into the force field is a key here. And enabling the use of Bayesian inference as a framework for making force field science decisions. I won't talk so much about this, but my student Owen Maiden has posters on 2 different aspects of this effort. So look for those. We'll be talking more about developing the infrastructure and looking at a QM and experimental data sets to compare to. So an important part is the SMIRNOFF format of these force fields. So what is the SMIRNOFF format? The SMIRNOFF format avoids the complexity of atom typing, where you have to decide how each atom depends on its chemical environment and state that in the force field. Instead, what it does is there's a process that goes through using some standard cheminformatics tools, SMARTS, chemical perception strings, that looks at each individual atom, each individual parameter. For example, you have a bond, you check and see, well, what are the atoms attached to this bond and what are their natures? And then you assign the parameters for that bond based on its chemical environment. Same thing for the van der Waals types of individual atoms, same things for the angles, that rather than having atom types where people have to think quite a lot about what are the different atom types in the system, you use just the chemical environment to decide on parameters for each individual parameter, each individual bond angle. And it turns out this greatly simplifies the system. Something like a GAF that might take 6,000 parameters can be reduced to something more like 300 parameters. So there's a publication on this. I'd encourage you to go to the website and check out the recent publication describing how this SMIRNOFF format works. So the open force field framework, we have a lot of tools here. You have some, say, initial force field you want to optimize. We feed things through the open force field toolkit, which is what is doing all the effort of, taking, say, a cheminformatics string, just expressing what the molecule is just in ASCII, and going through and identifying the parameters, assigning those, building topology files that can be used by other programs. And then those go into a system run by Force Balance currently, which essentially does regularized least squares optimization of the parameters. And those inputs could be quantum mechanical torsion terms, that's used a lot. Also, we've built this open force field evaluator that's a framework for calculating in a very automated way lots of physical properties. So all that goes in, an optimization is done to match all the data you fit in. And of course, this data comes both from both quantum mechanical data that we get working with MOLSI and the QC archive, and then also experimental property data, much of which is drawn from NIST's ThermoML. So a force field comes out of that. You can benchmark that, and then we repeat the process again with different data sets. And once we have the benchmarks and we can characterize this, then we can release one of the open force fields. So currently available open force fields, the original one was SMIRNOFF Frost. So what is this? It's a minimal amber compatible general small molecule force field, originally developed by Merck Frost. With excellent coverage of dry chemical space. And so originally this Merck Frost force field was developed. And so what we did, especially with the help of Chris Bailey, is to decrease the complexity down to about 300 lines. That just 300 lines can cover essentially all of small molecule chemical space. That doesn't guarantee that the parameters are perfect, but they are, about as good as GAF, maybe a little bit worse. But that's not what we generally release now. That was our starting point for the optimization. So PARSLEY was our first real optimized force field, a code name for the first generation of optimized small molecule force fields. So it results from a refit of the SMIRNOFF Frost to large sets of quantum mechanical data and assigning the parameters using direct chemical perception using the SMIRNOFF specification. So there have been several releases of PARSLEY so far, an initial one that took initial quantum data set, and then an addition of 1.0, an addition of a number of valence terms and torsions and propers, where we discovered molecules that the torsions were not really well fit, and then open force field 1.2.0 for learning from a lot of these lessons, where we increased the parameter quality across the board by dramatically improving the data set we used to fit, improved treatment of a number of groups like phosphonate groups, things like improved torsions for molecules with single bonds between divalent nitrogen and trivalent nitrogen. The point is as these are being used, we can identify weaknesses and go through and improve these a lot. An important thing to remember is that the thing that can go wrong the most when you're dealing with all possible drug space, we have a lot of different chemical interactions, is getting the torsional propensities right. If you get those right, those wrong, and those vary quite a bit from molecule to molecule, then even if you have good interatomic potentials, you've got problems there. So that's been sort of the initial focus on. I'll talk more about the next steps after this. So PARSLEY was a significant improvement over our initial amber frost. So what I'm graphing here is the delta E, the change in energy over different between different conformations over hundreds of different of molecules, and looking at all of these energetic differences compared to the quantum mechanical energy differences in vacuum. So as you can see, what you want to have is you want to have as big a bump in the center as possible. So as we've gone through, going from SMIRNOFF, open force field 1.0 to 1.2, we've been minimizing this configurational error between in over a very wide set of molecules. And there's a lot of details you can read about on the open force field webpage. There's a preprint of PARSLEY right now that's that you can find on ChemArchive, and it's also linked from the website. And so just a little more detail on what some of the benchmark assessments are, looking at geometry optimization and take the molecular geometries, you optimize them, start with the QM geometry and optimize with different force fields and see how far it goes, comparing these energies. as I've mentioned, seeing how far the conformational difference from one conformation to the next differs from quantum mechanics, how much the geometry in vacuum differs from the quantum mechanics, and also looking at energy versus not RMSD, but another measure that essentially looks at the difference between molecules in torsion space, which ends up being a little less size dependent. So what we can see is that, again, as you've gone, as we've improved the generations, this is all over about a year, we're getting significantly better energies and geometries for our molecular data sets. And right now, with these improvements, it's competitive with essentially the other general molecular force fields. If you look at the same sorts of graphs of deviations in energies and geometries, you can see that we're essentially doing better than everything except OPLS E3, Schrodinger's proprietary force field, which they've been working on for 10 years, looking at a lot of different geometries. So we might have a little bit of work to go there, but it's already as good as any existing open, any existing force field that is generally open and can be used by that's not proprietary. And this is all in 333 lines of parameters. We're expressing everything because we don't have to have a different torsion if you have 4 different atom types. You only have to have a different torsion that can recognize different chemical environments. Now, all I've been talking about so far is sort of the geometry matches, but of course now we have the system set up. Although we have not done any optimization yet, we have everything set up to do rapid evaluation and benchmarking of parameters. So what we've been focusing on for pure liquid properties is density, dielectric constant, and heat and vaporization. But very importantly, which I don't think has ever really been done in the testing of force fields, and certainly not the optimization of force fields, is looking at mixture properties. Because really, if you're interested in biomolecular force fields, things that are, can interact with proteins and water, then you want to be able to get mixing enthalpies and excess molar volumes right. So we've been testing those. And so, PARSLEY so far is getting essentially, equally good results as any existing force field before any parameterization so far. So this is something where we will be following up with optimizations later on. One thing that's really exciting, pharma is paying a decent chunk of the bills for this project. So one thing they're very interested in is using these force fields in protein ligand binding. This is why being good chemical space coverage is important, because you want to be able to say, I have reasonable parameters for any crazy drug molecule that my medicinal chemist can come up with. So this is some work in progress. This is protein ligand binding for energies, benchmarking components. And there's a lot of detail here over exactly what we're doing. A lot of this is done by a postdoc, David Hahn at Janssen Pharmaceuticals. And if you go on the Open Force Field webpage, there's a video describing this all in more detail. But we found that even already that if you look over of hundreds of different molecules in a dozen different target areas, that the free energies of binding are accurate within about 1.4 kcals per mole, and the majority of the perturbations deviate less than 1 kcal per mole from experiments. So this is very encouraging that even without optimizing the non-bonded so far, just by getting the torsional preferences right, we're getting results that are quite good and are essentially statistically indistinguishable from essentially all the other force fields out here. So this is the sort of thing even at this point can be used for drug design. And just as an example of how things have evolved, this is for one particular data set, thrombin inhibitors. And if you look at sort of the evolution going from GAF1, OPLS2, these are existing force fields. And then our SMIRNOFF frost behaved, roughly the same as GAF2, maybe slightly better. Just doing the improved torsional fitting gets, better match between experiment and predicted free energies. And so we're very encouraged by, what's happening so far, and before we've even, started to optimize the non-bonded energy. So planned larger initiative efforts. So now we're at the stage where for the next versions, we're going to be fully incorporating physical properties into optimization. Especially improved mixture properties. That's what we want to try to get right. But also optimizing free energies of solvation, transfer, and binding, free energies between various different solvents. We're collaborating with other force field developers and automating benchmarking, collecting benchmark data, and SMIRNOFF support for other force fields so people can implement this within their own force field efforts. Recently funded NIH RR1 with the goal of developing completely self-consistent biomolecular, small molecule, and polymer force fields. So you can easily treat covalent ligands because the covalent adduct is parameterized just the same as the biomolecule. Support for non-natural amino acids, consistent protein, nucleic acid, lipid, sugar parameters for heterogeneous systems. So you don't have to worry about matching one force field for sugars to another for nucleic acids, to another for lipids, because it's all parameterized self-consistently with the same parameters. Molecules is molecules. And finally, next generation force fields, working to provide clear evidence for or against alternative functional forms because we have this infrastructure where we can easily test things, and especially combining these efforts with machine learning potentials, especially for things like torsions. So please visit the website to check out more about this. And I would love to get any questions, send me emails if you have any questions about how this is working, how you can participate, and how to be involved. And thank you very much.